So in this video, we're going to talk about the role that radicals play in the world around us, and then we're going to talk about polymers, which is one topic you may see on the ACS final. So the first topic we're going to talk about is our atmospheric chemistry. So CFCs are a class of compound known as chlorofluorocarbons. So typical examples of CFCs would be something like CFCl3, CF2Cl3, Cl2, where they're made of carbon, fluorine, and chlorine. And these were developed as refrigerants for refrigerators, for air conditioners, for car air conditioning systems. And they tend to be pretty stable in the normal atmosphere. But when they evaporate, they begin to encounter more UV rays. And those UV rays decompose them into radicals. So both of these compounds are known as freons. So let's look at one of them. Let's look at our freon 12, CF2Cl2. So I want F2Cl, and I want to show one carbon-chlorine bond. So with UV light, which it encounters when it goes, up past the stratosphere, up into the stratosphere, we can get homolysis of this bond to start creating radicals. And what those radicals will do is that they'll interact with ozone in the environment. So ozone is O3. It comes from the reaction of oxygen. And it's very important for shielding us from UV rays. So the O3 molecule absorbs UVB radiation, so it plays an important role in preventing cancer, which can come from exposure to UV rays. And so maintaining the protective ozone layer is incredibly important. Now the problem with CFCs is that when they decompose, as I've already shown, when we have this chlorine, it reacts with ozone, I'm not going to show the mechanism, to give us this chlorine monoxide and oxygen. So we've already lost ozone in this reaction, but they're even worse than just one equivalent of CFC reacting with one equivalent of ozone, because this chlorine monoxide will react with oxygen radicals, which exist from the production of ozone, and they'll form oxygen and additional chlorine radicals. So because radical processes are often chain processes, where the initiation of one radical leads to many, many, many radicals, a small amount of a CFC can react with a lot of ozone. So CFCs were incredibly widely used because they were less flammable, they were less hazardous to people than the previous refrigerants being used. But in the 1970s, two scientists at UC Irvine, Rowland and Molina, learned from a scientific talk that CFCs were really in the atmosphere pretty much indefinitely and wanted to figure out what was really happening to them. And so through this study, they figured out that ozone was really being depleted at a very, very rapid rate. And so they reported this result. There was a lot of pushback, but the world came together and through the Montreal Protocol really reduced and then banned CFCs from being used. And so they're really used significantly less than they used to, although we still see countries using them. In terms of refrigerants, we've replaced CFCs with HFCs, which are hydrofluorocarbons. So that would be something like C2H2F4. And so these have very similar properties. They don't have these carbon-chlorine bonds, which are the ones that are affected by UV radiation. However, these compounds are incredibly potent greenhouse gases, significantly more than carbon dioxide. So research has been done to reduce the ability of these compounds to act as greenhouse gases. And so one example of the next generation has this olefin for alkene. It has still carbon, hydrogen, fluorine, but the chemical structure means it's a less potent greenhouse gas. However, with these highly fluorinated compounds, there is also concern about how they impact people's health and also environmental health because they don't degrade very much. So that means over time, they're going to build up in our environment, and we don't really know what the health impacts of that will be. So we've solved one problem, but we have a long way to go in terms of making them part of a more sustainable future. So our next topic is going to be biological in nature. So we're going to start by looking at these fatty esters, which are derivatives of fatty acids. They're part of triglycerides, which are the most common types of fat that we see in our diet. So olive oil, butter, lard, coconut oil, all of those are composed of triglycerides. And so when you have these fatty esters, we notice that we have a lot of cis double bonds in unsaturated fats. And these cis double bonds, these compounds with cis double bonds, can react with radicals. And the position they're going to react at is going to be the position that gives the most stable radical, the one between the two double bonds, which gives an allyl stabilized radical. So if we have a radical around, that's going to react in just the same way that we've seen when we're doing our allylic bromination to give this stabilized radical. And the stabilized radical can react with oxygen. So you might remember from general chemistry that oxygen, O2, actually has a triplet diradical structure. And you'd have to look at that using MO theory. So I'm going to draw oxygen in a way that highlights that radical characteristic. So I'm not going to show the typical double bond, which it does have, and I'm instead going to show the radicals. So this is going to react, and it's going to react with our radical in a way that creates the most stable product again. In this case, that will be the product with this conjugated double bond. Now this is a highly reactive radical that will react with other protons on other fatty esters. This process will repeat, will form many radicals, will also form these peroxides, which can also decompose, so there's going to be a lot of decomposition here. The two impacts of this are going to be, one is food related, so unsaturated fats like olive oil, vegetable oil, things like that tend to undergo this process over time in air. It's accelerated when those oils are exposed to light, which is why olive oil often has, not a clear container, but often is like green or brownish. It's also accelerated by heat, which is why fry oil gets that like characteristic smell. And so when this autooxidation happens, these oils go bad, they're called rancid, and this is something you may have experienced if you've ever worked, in a food environment. This doesn't happen with saturated fats because they don't have the double bonds. So this is why in many industrially processed foods you see, hydrogenated oils, shortening, things like that, because they allow products to have a longer shelf life. If this happens in the body, it can be very dangerous because we're creating radical chain processes, and obviously the mechanisms of the cell are very sensitive, and having these radical reactions can cause significant cell damage. So to counteract that cell damage, to counteract those radicals, this is where antioxidants come in. So antioxidants are molecules that react with radicals, but the radicals that they form themselves don't perpetuate the radical chain because they're stabilized. So if we look at two really common antioxidants, the first is vitamin E. This is something that you're obviously going to find in the body. Also, it's found in vegetable oils. And so the radical that forms when it reacts with the radicals shown above is going to look like this. At the phenol, we're going to have this O with a radical on it. And because of the presence of the benzene ring, we can imagine that that radical is stabilized by resonance. So the same thing happens in BHT. You have the same phenol structure, which again can form a very stabilized radical species. BHT is added to a wide variety of products, including foods, fuels, etc., in very small amounts to prevent radical formation, including some organic solvents that have a tendency to form explosive peroxide compounds. And this is why you need vitamins like vitamin E, vitamin C in your diet to help promote this antioxidant behavior. A lot of companies have used this science to argue that, vitamin E, vitamin C can help counteract aging, it can deal with all sorts of diseases, but there's really limited evidence that any of that works. So in general, you should be skeptical of, any science that says one food or one ingredient can fix a variety of diseases, can help counteract normal biological processes.